Hemant Kumar, is it audible? Hemant Kumar? Hemant, is it audible? Hello, Hemant.
Hello, yes, sir. Hello, yes, sir.
Slides, are they
Yes, sir,
visible?
we are in. Yes, sir, visible.
Yeah. Okay. So we have still 6 participants. Time is already 1. You need to be regular. So in the last class, what we had seen is regarding the paging concept and segmentation with paging. And if you see the slides, so then we have separate diagrams. So for the explanation of the paging concept, where the logical memory will be divided into so many parts, okay, so many blocks, and each and every block we call it as a page. Similarly, the physical memory of the main memory or the RAM is also divided into various blocks, okay, of fixed size. Those are called as page frames, okay. So using paging, like we have seen some diagrams, and after paging we had seen a segmentation, okay, and we have also seen the segmentation with paging. So after those concepts, the next concept is virtual memory. So we call it as VM. So VM stands for the virtual memory. So as the name itself indicates, like this is a virtual memory, okay, not physically present. So but the user will assume that he has got a huge amount of RAM, okay. So this virtual memory is an illusion of the physical memory. Remember this. So this virtual memory is a feature of operating system where the user will have an illusion that he has got a large amount of RAM. I repeat, so this virtual memory is nothing but a illusion of the physical memory where the user will assume that he has got a huge amount of RAM. Okay, so the RAM size is somewhat larger. Okay, so but that will not be the case actually. So when you compare the size of RAM and the hard disk, like which one will be of larger size according to the available modules in the market? Obviously, the hard disk will be of larger size, like in terms of GBs and in terms of terabytes. So, but the RAM size will be limited. Okay, so we have a finite amount of size of RAM, like in any system. So, but the hard disk space will be very much larger or huge. Okay, like in case of virtual memory, so what user assumes is he has got a huge amount of RAM and he can write his program of larger size. Okay, so whatever may be the size of the program or the process or what user has written, okay, this process will be able to be stored in a large amount of RAM. Okay, so the user will be under the illusion. Okay, so this virtual memory is nothing but a illusion of the physical memory or the main memory or the RAM. Okay, uh, like it is done by treating a part of the hard disk as the main memory. Okay, so like here the concept is a part of the secondary memory or a part of the hard disk will be considered as the main memory itself. Okay, like in virtual memory, the user can store the processes with a bigger size than the available RAM. So for example, suppose if the RAM size is say 1 GB, okay, understand this. Suppose if the RAM size is 1 GB and if the user program is say 2 GB, okay, like even then, I can go for the execution of 2 GB of process. Okay, even though the available RAM is of size 1 GB and the RAM size is smaller than the process, right? Even then, I can execute a bigger process in a smaller size RAM. Okay, so how it is done actually? Okay, how we are able to execute a 2 GB process or program in 1 GB of RAM. Okay, there lies the actual concept of this virtual memory. So here what we do is, instead of loading a long process of say 2 GB, right, in the main memory, so what we do is the OS loads various parts or various sections of more than one process in the main memory. Okay, say suppose if I have a say 2 GB of process means, okay, as a whole 2 GB of process will not be loaded at a stretch in the main memory. Like as I said, this main memory is very much limited. Okay, so we have a finite size main memory. Hence, I cannot reserve the whole of the main memory for only one process. Okay, so for that, what we do is I'll be loading small parts of more than one number of process, so that I can accommodate more than one number of process inside the main memory. Okay, so but what what we think is, I have got a huge amount of RAM, hence I can write say 1 GB of program, or I can write even 2 GB of program or n GB of program, and my program will be effectively executed by the CPU. Okay, so but that will not be the case actually. Okay, and here the role of virtual memory is very much vital here. So this virtual memory is implemented using so we have basically two approaches. Next, we have to implement this virtual memory. So we have something called as demand paging and demand segmentation. So we look at this demand paging and demand segmentation along with the diagrams and examples in the upcoming slides. But for now, you understand that this virtual memory is nothing but a illusion of the physical memory, where the user assumes that he has got a huge amount of RAM available. And even though the RAM size is less, I can execute a program, right, of a larger size when compared to the size of a RAM. Okay, and that has been achieved by not loading the long process at a stretch in the main memory. Okay, rather I'll load small parts of that particular process, okay, like into the RAM, and those small parts can be executed by the CPU. Okay, yeah. So for your better understanding, and apart from the syllabus, like I try to include these two examples, okay, so as to explain the concept of virtual memory, so you can have a better idea regarding the concept of virtual memory. So that let us see the example one. Okay, suppose if OS is in need of say 300 MB of memory, right? Suppose if the OS is in need of 300 MB of memory, so but we only have 50 MB of RAM. Okay, so the RAM size of only 50 MB. So but the OS is in need of 300 MB. Okay, like in that case, what OS will do is OS will be able to set up extra amount of 250 MB required. Okay, using a program called as a virtual memory manager. So this VMM stands for virtual memory manager, which will take care of setting up of this extra 250 MB of virtual memory. Okay, so this virtual memory manager will manage this 250 MB of memory, wherein this virtual memory manager will be able to create a file of 250 MB in size, so as to have the extra amount of memory needed for the operating system. So now, so now the OS can assume that it has got a memory of 300 MB. Okay, hence the OS can execute its program. So, but in real, okay, the RAM size is only a 50 MB. Okay, so the real space in reality, in reality, the RAM size is of only 50 MB. So, but due to the action of this virtual memory manager, it will create an extra space of 250 MB of memory in the hard disk, and that we call it as the virtual memory. So now our OS will assume that it has got a RAM of size 300 MB. So, but in reality, we have only the RAM size of how much? Hello?
50 MB.
50 MB. Okay, so this extra 250 MB is not really present, not physically present. Okay, so but it is virtual. Okay, how come it is virtual? Okay, how come it is an illusion? Because like in the hard disk only, some space is reserved, okay, means some space in the secondary memory or some space in the hard disk can be considered as the main memory itself. Okay, so here lies the real concept of this virtual memory. Means even though we have a lesser amount of RAM, so but still I can execute the programs or processes which are much more larger than 50 MB of memory, right? How it is possible? Because the use of virtual memory. Okay, and second example, like which justifies the existence of virtual memories. Suppose if the RAM size is 20 KB, okay, suppose if the RAM size is 20 KB and the hard disk is of size 100 KB, okay, and like as you can notice here, the size of hard disk is much more larger than the RAM size. Okay, so for simple example, right, let us take the RAM size of 20 KB and hard disk is of 100 KB, and if like a program is of size 60 KB, so then like as you can see that the program is of larger size when compared to the available RAM. Hence, I cannot store 60 KB of my program into the RAM. So for that, what I can do is, like initially, like we know that this 60 KB program will be stored in the hard disk. Okay, so the CPU cannot execute whole of this 60 KB, okay, of our program. Hence, what we do is, so this 60 KB of program will be broken down into 20 KB, 20 KB, 20 KB, and each and every part of this 60 KB program means like this. Each and every part of 20 KB will be loaded into the RAM, and the CPU can access the RAM and execute a particular part of the process. Okay, so like in this case, what user feels is like he has got a large amount of RAM, and my system, okay, like even though the RAM size of 20 KB, even then I will be able to execute a process or a program of size 60 KB. So, but here the actual thing, what is happening is, so this 60 KB of memory will be broken down into different parts, and each and every part of the program is called as the page, and I'll be loading each and every page, okay, one after the other into the RAM, so that I can execute each and every part of the process, right, or the program. Okay, so for simple example, the values taken here are our program is of 60 KB, right? Hence, 60 KB is not directly stored in 20 KB of RAM. Hence, this 60 KB will be divided into 3 parts. Each part is of 20 KB, and each part will be loaded one after the other, so that I can store the 20 KB of memory. I mean, this, what is that? 20 KB of program, okay, into the RAM, so that CPU can execute that particular part of the process. Okay, yeah. So like this is the actual figure like given in your textbook. Okay, so for the heading virtual memory, right? So the virtual memory is nothing but an illusion of the physical memory. Like here we have the process. Okay, so this process can be called as the logical address space, and this particular process will be divided into so many equal parts called as pages 1, 2, 3, 4, 5. So this process like has got 5 components in it, or 5 pages in it, and this page 1 and page 2 and page 5 are readily available in the memory. Okay, and we have this like this part is called as the memory, or the physical memory, or the main memory, or the RAM. And again, this RAM has been divided into so many equal parts or partitions, where each partition is called as a frame. Okay, and in the middle of this logical address space and the physical address space, or in the middle of this logical memory and the physical memory, we have one more unit by name MMU. MMU stands for what is it? MMU, Memory Management Unit stands for, this MMU stands for Memory Management Unit, whose main function is to convert the logical address into the physical address. Okay, yeah. So we have the logical address space of the process as shown here, and this like this logical address space has been divided into 5 different parts or components, like as you can see here, right? And among these 5 components, 1, 2, 3. So these 3 of these components are presently there in the memory. Okay, and actually where these components will be existing in the main memory or in the physical memory, this information will be maintained in something called as virtual memory manager. Okay, so this information is used by this like so-called MMU or memory management unit when it is doing the address translation from logical address to the physical address. Okay, so an instruction in the process will refer to a data or instruction, right, that is not available in the memory. Like in that case, okay, that particular component of a process can be loaded from the hard disk to the physical memory or main memory, and I can execute this particular section of the process. Okay, so like in between this logical memory and the physical memory, okay, so this MMU will be taking care of the address translation. Okay, and this will be obtained so by the MMU, and this will be able to convert the logical address into the physical address. Okay, suppose if the kernel or the OS is, say, searching for some data and that is not presently there in the memory, like in that case, so what OS will do is OS will be able to pick up that particular data or information from the hard disk, and that can be loaded into the main memory for execution. Okay, so we can explain this concept for virtual memory. And this like the basics of virtual memory is the non-contiguous memory allocation model. So like the meaning of this non-contiguous memory allocation model, right, is been actually shown here, where we are storing the different parts of the process at different locations. Okay, like as you can see here, the different components of a process, right, or a program will be not stored contiguously, or the different parts of the process will be stored in, say, adjacent memory locations, right, and these locations are not continuous. So for example, the second component is stored in say this frame, okay, and the last page is stored in the first frame of the main memory, etc. Okay, and regarding the address translation, we can go for this particular logical address to physical address translation, right, of the form component I, comma, byte of the ith process. Yeah. So the simple example according to the book, right, like on the basis of virtual memory operation. So for that, this particular figure is being mentioned, like along with some numerical values. So for this, the heading is logical address space and physical address space and address translation with respect to VM operation. VM stands for virtual memory. So what is the concept here is, so we have a process A, and this particular process A is been divided into how many parts? According to this diagram, what you can see, process A is having how many parts?
4.
Process A is been divided into 4 components, 4 parts, 4 partitions, A1, A2, and A3 and A4, and each and every part are having the logical starting address, and the size of each and every part has been mentioned along with the starting address of the memory area. So where the logical address space is from 0 to 16999, and here is our physical memory or the RAM, right, or the physical address space from 0 to 49999. Okay, and also you can see that like these different, say like different parts of the process A, right, are not stored in a continuous manner in the physical memory. Like as you can notice that, like this A1 is stored from here, and A2 is somewhere stored in the middle of the main memory, and this A3 component is stored somewhere here. Okay, so we have the mentioning of the logical address of A1, A2, and A3 and A4, along with the sizes of each and every part of process is also been mentioned, along with the starting address of the memory area. Okay, suppose if I have like to access an address of 3349, okay, so this 3 is always referring to the page number, and this 349 or higher order number will be representing the offset. Okay, Okay, so what this MMU or ATU? This ATU stand for address translation unit. Like it is as good as MMU, right? So you can call it as a memory management unit or address translation unit. Okay, so what this MMU or ATU will do is, like, it will consider this what is it, 3349 as 3 and 349. So where the higher order number will be representing the page number and the lower order numbers will be representing the offset. Okay, so here according to this, right, suppose if I say see the starting address of this third component, what is that? According to this particular table, the starting address of A3 component is how much it is? 38,000. So this 38,000 is being concatenated with which number? 349, where 349 is the offset. Okay, so once I add this 38,000, right, like the, I mean, this starting address of the third component of process, like so-called A3. Okay, so this 38,000 starting address of component A3 will be added with the offset number 349. Hence, I can obtain the actual physical address in the main memory. Okay, so here same thing is been shown here. Okay, and heading for this will be the example for the virtual memory. Okay, example of a virtual memory operation, right? It has been explained here along with the numerical values for logical address space and physical address space, and along with the address translation done by the MMU or memory management unit, like also called as ATU. ATU stands for address translation unit. Okay, like this is one more figure, right? Heading for this is address translation in virtual memory using paging. Like as we know that, so this virtual memory is nothing but the extension of the paging. Okay, hence heading for this figure is address translation in virtual memory using the paging concept. And here, not to forget, this virtual memory is nothing but the extension of the paging. Okay, so so what I can see here is, so we have here like so process P1 is there, and process P2 is there, and process P3 is there, and here the size of process P1. So this process P1 is been divided into how many sections, how many parts, how many blocks, how many pages? 0, 1, 2, 3 are the pages. Hence this process P1 has got 4 pages, and the process P2 is having 0, 1, 2, 3, 4 means 5 pages. So this process 2 is divided into 5 different pages, and process 3 is been divided into 0, 1, 2, 3, 4, 5 means 6 number of pages. Okay, so here like in the figure, basically we have how many processes? 3 processes, where some of the pages are already being present in the memory. Say for example, the second page of process P1 is present in which frame of memory? Frame number 1. Okay, similarly the say second page of process P2, right, second page of process P2 is present in 7th frame. Okay, and the first page of process P2 is present in which frame?
5.
5th frame. Okay, similarly, like if you look at the third process, so by name P3, the first page of process P3 is stored in 0th frame of main memory, right? Similarly, third page of process P3 is stored in 2nd frame, and 4th page of process P3 is stored in 3rd frame. Okay, yeah. So the memory is containing 8 number of frames from 0 to 7 it is. Okay, right? So you can take like these are the page tables along with the storage of various pages of these process P1, P2, P3 in various frames of main memory. And here is our RAM. Okay, and we have this the starting address. I mean, like, so we have here 0 to 7 number of frames. Okay, so this process P2 is currently executing. The instruction address of it is 2480. Okay, so this process P2 is currently in the execution. Hence, so this 2 will be always indicating the page number. and the offset is 480. Okay, so we can have the accessing of the particular page 2, and in the particular, like the particular page 2, the offset is 480 is the offset. Okay, suppose if I say look at this page 2. Okay, so this page 2 is stored in which frame? 7th frame. Hence the OS of kernel will be able to access the 7th frame. Okay, and you can also notice that offset is remaining same. Okay, so this address of 2528, okay, is been analyzed as, so this MMU, what it does is MMU uses the process P2's page table for address translation. Like here it is. Okay, here it is. So the MMU will view the data address as the pair 2, 480, where this 2 is indicating the page number and this 480 is the offset. So here 2 into the size of each and every frame is 1024 bytes, right? Along with the 480 being the offset, right? I can access the actual physical address will be 7 into 1024 plus 480. So where the offset is being maintained the same. So, but this page number 2 is being now replaced with the frame number. Frame number, what is it?
7.
7. Okay, so now the actual physical address of this 2480 will be the frame 7, right? And in that frame 7, the offset will be 480. So now I can access this particular logical address as 7 into 1024 plus 480. So the 480 byte in frame number 7 is being accessed. Okay, and you can also see the list of free frames. Okay, so where the frame number 6 in the main memory is being like it is free. It is okay. So this page 6 is not been occupied by any of the page. Okay, yeah. So suppose in the examination, again the question is, so with the relevant diagram, explain the address translation in virtual memory with paging means. You can take the example of this particular figure where we have here the 3 number of process, where each and every process, right, it has been divided into so many pages, and some pages will be stored in the main memory. So whereas some frames are being left free. Okay, right, and for any random address location, okay, how we are able to convert so this logical address into the physical address using this unit, hardware unit called as MMU. MMU stands for memory management unit, right, whose main function is to convert the logical address into the physical address. So this MMU is one more name. What we have seen in the previous diagram is MMU is also called as ATU.
Translate.
Yeah, ATU stands for address translation unit. Okay. Yeah. So like after we understand the meaning of paging and segmentation, so we can have these many comparisons. Okay, like bifurcation between the paging and segmentation. So you can analyze by yourself. So once we understand the meaning of paging and segmentation in depth. So what we have seen till now is like this paging allows the memory to be divided into fixed size block, means fixed size partitions, fixed size parts, where each and every part it is called as pages. Okay, and in case of segmentation, again the memory has been divided into variable size blocks, and in this case, like these variable size blocks are called as segments. Okay, so this paging suffers from internal fragmentation, right? Again, the meaning of internal fragmentation it has been rightly written here. That means what? Memory allocated to the process is not fully utilized by the process, and this will happen in case of paging. And in case of segmentation, this suffers from external fragmentation. Again, the meaning of external fragmentation is available memory blocks or parts or space are too small, okay, are very small, so that I can allocate this particular small space for a particular program. And also the memory spaces are not continuous. So this will be leading us to the external fragmentation, which occurs in segmentation. Like similar to that, like they have here so many points with respect to the paging and segmentation, and all these are very much easy. So once you read this, you will be able to understand it in a better way. So for example, in case of paging, so we have the use of something called a space table. Okay, in case of paging, so we use the page table, which will give us the information regarding which page, right, of a process is stored in which frame in the main memory. Okay, like in case of paging, we take the help of this data structure by name page table. Okay, and this page table is residing in main memory itself. Okay, like remember this point, right? And in case of segmentation, we use something called a segment table, whose main function is to map the logical address to the physical address. Okay, so we have the use of page table in paging, and we have use of segment table in segmentation. Okay, so likewise, so you can see here so many comparisons with respect to the paging and segmentation functionalities. So you can analyze this. That's very easy. No need to worry. So next concept is demand paging. Okay, like as the name itself indicates, like if and only if the page is being demanded by the CPU, then only we can load that particular demanded page into the RAM so that CPU can be accessed. Okay, so a page is usually brought into the RAM, okay, or main memory only when it is needed or demanded by the CPU. Okay, suppose if this CPU is not demanding, say for page 3, then that particular page 3 will not be loaded into the RAM. Okay, right? Similarly, if any page is demanded by the CPU, then only the OS will be loading that particular page into the RAM. So until and unless the CPU demands for a page for execution, okay, till then that particular page will not be loaded into the RAM. Hence, we call this as the demand paging. Okay, like demand paging also, we divide the program into fixed size block, and those fixed size block are called as pages. Okay, similarly, the RAM is also being divided into equal size partitions, equal size blocks, okay, equal size parts, where they're called as frames. Okay, and again, same sentences, size of the page will be equal to the size of the frame. Okay, so the blocks, there are like the blocks which are there like in the program or of the process are called as pages, and the blocks which are there in the main memory or in the RAM, they are called as page frames. Okay, so like in demand paging, what we do is only the required pages will be loaded. Okay, understand this, right? In case of demand paging, as name itself indicates, only the demanded page, okay, or only the requested page or only the required pages will be loaded into the main memory for execution. Okay, so first the initial pages of a program will be loaded, okay, and we can start the execution. So the remaining pages will be residing in the hard disk itself. Okay, and upon the request of any page, okay, then only those pages will be stored from hard disk to the main memory for execution. Okay, so in the hard disk, like you can reserve some particular amount of space, okay, where these pages will be stored, and that particular space we call it as swap space. Okay, so this swap space is used, okay, in the hard disk, where I can store the remaining pages of the process, and only on demand. Okay, I repeat, only on demand those pages will be moved from hard disk to the RAM for execution. Okay, hence the name demand paging. Okay, so this same thing is mentioned here. So this demand paging is a concept that allows execution of process by loading only few pages. Means not all the process will be loaded at a stretch. Okay, initially only few pages that are required to start the execution will be loaded. Okay, and the remaining pages are brought into the memory only when they are required. Only when they are requested or only when they are demanded. Okay, hence we call this as the demand paging. Okay, like in case of demand paging also, any process will be divided into blocks of equal size. Those are called as, what are they called? Different parts of the process. Each part is called as pages, and obviously the physical memory or address, or also the physical address space or RAM or physical memory is also being divided into equal number of blocks, partitions of equal size, and they are called as frames, right? Or page frames. Okay, and the size of the page and the size of page frame are same. Okay, so regarding the logical address, so the logical address consists of the page number and offset, and the physical address is formed by using the frame number and the offset, exactly similar to that what we did in the paging. Okay, so the logical address will be having two parts. Okay, first part will be the page number, second part will be the offset. Okay, and in case of the physical address, this physical address is also having two parts. First part will be the frame number, second part will be the offset. So we have something called a space table that will be used in the demand paging. Okay, I think we are done with this demand paging. Like, so what does this demand paging means? Demand paging is nothing but what the pages, right, of a process will be loaded into the RAM only if the CPU is demanding for that particular page. If not, those pages will be kept in where do you keep those pages initially? Hello, anybody there?
Yes, sir. Yes,
So
sir.
So like in case of demand paging, what I said was, suppose if the pages are not being demanded by the CPU, so then where will be those pages kept? In the hard disk. Okay, so if and only if the pages are being demanded or requested by the CPU, then only those pages will be moved from where to where? Hard disk to the main memory for execution. Okay, so for the implementation of the demand paging, like I need to have something called as a page table to be used, having these many fields. Okay, so what is the first field here? First field is nothing but the valid bit. So this valid bit, like as name itself indicates, like whether the like say that particular page is present in the main memory or RAM or not. Okay, suppose if the requested page by the CPU is present in the RAM, means this valid bit will be highlighted as 1. Okay, so this 1 indicates that the page requested is currently there available in the RAM. Suppose if this valid bit is equal to 0 and that 0 indicates that the requested page is not available in the RAM. Instead, where will that be present?
Hard disk.
Hard disk, exactly. So this valid bit is nothing but a single bit, where this bit can be either 1 or 0, where 1 indicates that the requested page is currently there in the RAM. Okay, and if the valid bit is equal to 0, means that particular page requested by the CPU is not currently available in the RAM. Hence, I need to bring that particular page from hard disk to the main memory for execution. Okay, so we can have the indication of the validity of the bit, means whether the page is present in the RAM or not. Okay, so we have this row number or page number as like this page indicates the row or page number. Okay, say for P1 page, right? So whether the P1 page is present in the main memory or not, that is indicated by the valid bit. And second field is the page frame. Okay, so this page number P1, right? So process P is stored in which frame? That is indicated by the second column, second field. Okay, that says page frame. Okay, so this page frame is the second field in the page table, which contains the number of the page frame occupied by the page. Means this particular page P1 of any process is stored in which frame in the main memory? Fourth frame. right? So for example, right, example I've taken, right? So this second field, so-called page number, will indicate in which frame this particular page is stored, right? Similarly, the third field is called as production information, okay, or the production bit, whose intention is